Imagine a spacecraft drifting through the darkness between stars. Outside its hull, the surrounding radiation is only a few degrees above absolute zero. Inside, the cabin remains warm enough for people to breathe, sleep, and work. Liquid water moves through pipes. Batteries hold their charge. Propellant remains ready inside narrow metal lines. Computers continue processing thousands of signals every second. None of that warmth exists naturally. Every comfortable degree inside the spacecraft is being created, moved, trapped, or released by machinery. Electric heaters protect components that would otherwise become too cold to function. Coolant pumps carry waste heat away from electronics that could still overheat, even while the darkness outside approaches the coldest temperature nature normally allows. Insulation slows heat from escaping. Radiators point toward empty sky. A fading power source keeps the entire balance from collapsing. And that is the strange truth about the cold of deep space. It would not freeze an astronaut instantly. Vacuum can preserve warmth surprisingly well because there is almost no matter available to carry heat away. But that same emptiness removes every natural system that keeps temperatures stable on Earth. There is no air to spread warmth, no wind to cool an overheating surface, no atmosphere to soften the difference between sunlight and shadow. One side of a spacecraft can become dangerously hot, while another becomes dangerously cold. A battery may need heating, while a nearby computer needs cooling. Farther from the sun, every available watt becomes more valuable, while the machines producing those watts slowly weaken with age. Tonight, we are going to follow that cold outward, from the shadows around Earth to the regions where sunlight becomes almost useless. We will see what happens to human bodies, spacecraft materials, fuel lines, batteries, and abandoned machines when warmth becomes a finite resource carried through an almost endless dark. Before we begin, if you enjoy calm journeys through space and the science hidden inside them, you can take a moment to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us return to that spacecraft. The cabin may feel still, but energy is moving through it constantly. Warm air is being pushed through ventilation ducts. Heat from computers is passing into metal plates and cooling pipes. Electric current is warming small resistance heaters attached to batteries, valves, and instruments. Beyond the walls, radiator panels are releasing infrared energy into space. Every one of these processes follows the same basic rule. Heat moves from regions with more thermal energy toward regions with less. On Earth, that movement happens in several ways at once. Touch a cold metal railing, and energy leaves your hand through direct contact. This is conduction. The particles in your warmer skin transfer energy into the cooler particles inside the metal. Stand outside on a winter day, and moving air carries warmth away from your body. This is convection. Air near your skin becomes warmer, moves aside, and is replaced by colder air that can absorb more energy. Water performs the same process even more effectively, which is why cold water can lower body temperature much faster than cold air. The third pathway is radiation. Every object warmer than absolute zero releases electromagnetic energy. At ordinary human temperatures, most of that energy leaves as infrared light, invisible to our eyes, but easily detected by thermal cameras. Radiation does not require air, water, or physical contact. It can cross an empty vacuum. It is how sunlight reaches Earth, and it is how a spacecraft eventually releases nearly all of its unwanted heat. Inside the cabin, conduction and convection remain possible because the spacecraft contains air, solid structures, and circulating liquids. Beyond the hull, the situation changes. There is almost no surrounding matter available to touch the vehicle or carry its warmth away. Conduction into the environment becomes negligible. External convection disappears almost entirely. Radiation remains. That difference changes everything about thermal survival. A spacecraft cannot simply open a vent and allow cold outside air to cool its computers. There is no outside air. A freezing component cannot be warmed by a natural breeze carrying energy from somewhere else. Heat stays concentrated unless the vehicle deliberately moves it. The spacecraft must collect unwanted warmth from one location, transport it through metal or liquid, and deliver it to a surface that can radiate it into the sky. At the same time, it must prevent essential warmth from leaking away from batteries, propellant lines, instruments, and living spaces. This balance is never permanent. It changes whenever the vehicle rotates, enters shadow, activates a transmitter, starts a pump, fires a thruster, or loses another fraction of its electrical power. Even a sleeping crew alters it. Each human body releases heat into the cabin. Moisture enters the air with every breath. Fans keep that air moving because warm and cool pockets do not circulate normally in weightlessness. Cooling equipment must then remove the heat produced by the very people it is trying to protect from the cold outside. The result is a small, artificial climate, traveling through an environment that provides no natural climate at all. And before we can understand how fragile that climate becomes, we need to define the temperature of the emptiness surrounding it. Because deep space does not contain one simple cold temperature waiting to enter through the hull. Its thermal environment is made from radiation, scattered particles, distant stars, and the energy carried inside the spacecraft itself. The famous temperature associated with cosmic space describes only one part of that environment, an ancient field of radiation that has been cooling for almost the entire history of the universe. That faint radiation is where the deeper journey begins. A thermometer on Earth is never measuring air from a distance. Its sensor is being struck by molecules every fraction of a second. Faster-moving molecules transfer energy into it. Slower-moving molecules receive energy from it. After enough collisions, the sensor approaches the same temperature as the surrounding air and gives a reading we recognize. That process becomes much weaker in a high vacuum. With very few particles nearby, there are far fewer collisions to bring the thermometer into balance with its surroundings. The instrument may still be warm from the spacecraft that released it. It may absorb light from a nearby star, infrared energy from a planet, or heat radiated by the spacecraft itself. Its reading mostly describes the thermometer's own condition. Temperature is a measure of microscopic energy. In a gas, it reflects the average motion of atoms and molecules. In a field of radiation, it describes the pattern and energy of the photons filling that field. A physical object has its own temperature, determined by the energy stored within its material. This is why the phrase "temperature of space" needs care. Several thermal environments can overlap in the same location. Sparse gas may have one particle temperature. Starlight may contribute another source of energy. A spacecraft carries internal heat from its electronics and power system. Faint radiation arriving from the distant universe adds a background. That ancient background is called the cosmic microwave background. It fills the observable universe in every direction and is one of the oldest forms of light we can detect. For the first few 100,000 years of cosmic history, the universe was hot, dense, and filled with charged particles. Light could not travel far before colliding with free electrons. As expansion continued, the universe cooled enough for electrons to join atomic nuclei. This happened roughly 380,000 years after cosmic expansion began. Once neutral atoms formed, light could travel much more freely. Those photons have been crossing space ever since. The expansion of the universe has stretched their wavelengths over billions of years, lowering their energy until the original glow now appears mainly as microwaves. The first strong observational evidence arrived unexpectedly. In 1964, radio astronomers Arno Penzias and Robert Wilson were working with a horn-shaped antenna in Holmdel, New Jersey. They encountered microwave noise that remained present regardless of where the antenna pointed. They checked the equipment, removed possible interference, and even cleaned material left inside the antenna by pigeons. The signal remained. A group at Princeton University was preparing to search for this leftover radiation. The teams connected their findings, and the result was published in 1965. The persistent noise was light from the early universe. Later spacecraft measured it with far greater precision. The Cosmic Background Explorer, launched in 1989, carried the Far Infrared Absolute Spectrophotometer, usually called FIRAS. It compared the background radiation with an extremely precise reference source and found a nearly perfect blackbody spectrum. A blackbody is an idealized object or radiation field whose energy follows a specific pattern set by temperature. The cosmic background matches that pattern with extraordinary accuracy. Its present temperature is approximately 2.725 Kelvin, equivalent to about minus 270.4 degrees Celsius. That number belongs to the radiation field. Individual objects can remain far warmer for long periods. A sunlit surface may become extremely hot. A shielded telescope can stay deeply cold. A working spacecraft may remain near room temperature because its equipment continually releases energy. An object changes temperature according to its energy balance. It absorbs radiation from nearby sources and receives heat from anything operating inside it. At the same time, it emits infrared energy. Its temperature rises when incoming power exceeds outgoing power and falls when the balance reverses. Over enough time, it may approach an equilibrium where the two rates become equal. The final temperature depends on surface material, orientation, distance from stars, internal power, and nearby objects. Two spacecraft occupying the same region can settle at very different temperatures if one reflects most incoming light while the other absorbs it. The darkness around a spacecraft, therefore, has no single temperature waiting to enter through the hull. It contains a weak radiation field, scattered particles, and distant sources of energy. The spacecraft responds to all of them while carrying its own heat. With so little matter available to touch the vehicle, nearly all of that warmth must eventually escape in another way. Radiation is only one of the ways a warm object can lose energy. On Earth, heat usually moves through several pathways at once, and the fastest one often depends on what surrounds the object. Place your hand against a cold metal railing, and energy passes directly from warmer skin into cooler metal. This is conduction, the transfer of heat through physical contact. Metal feels especially cold because it conducts energy away from the skin much faster than materials such as wood or fabric. Cold air removes heat through convection. Air touching the body warms, moves away, and is replaced by cooler air. Wind speeds up this exchange by continually bringing new air into contact with the skin. Water performs the same process much more effectively. It is far denser than air and can absorb much more energy before its temperature rises. Water at 15 degrees Celsius can cool a person far faster than air at the same temperature. This is why prolonged immersion can become dangerous even when the water does not feel close to freezing. A body also releases infrared radiation from its surface. This happens continuously, whether the person is standing in a room, swimming in water, or floating in a vacuum. Nearby walls and objects radiate energy back. So the net loss depends on the temperature of everything within view. Vacuum removes most external conduction and convection. There are too few atoms nearby to collide with the skin, often enough to carry away substantial heat. Infrared radiation continues, along with evaporation from exposed moisture, but the rapid cooling associated with winter wind or cold water is absent. Sudden exposure would still become life-threatening within seconds. The pressure inside the lungs would be much greater than the pressure outside. A person would need to allow air to escape rather than holding their breath, because expanding gas could injure delicate lung tissue. Oxygen already carried in the blood would support awareness only briefly. Useful consciousness would probably be lost after roughly 10 to 15 seconds as oxygen-poor blood reached the brain. Low pressure also changes the behavior of water. When surrounding pressure falls far enough, liquid can begin turning into vapor without first becoming hot. This process is called ebulism. Moisture on the tongue or surface of the eyes can begin to vaporize. Water held inside blood vessels and deeper tissues remains under pressure from the body, so the entire body does not begin boiling. A rare accident during the early space program provided a real example. In 1965, spacesuit technician Jim LeBlanc was participating in a vacuum chamber test at NASA's Manned Spacecraft Center in Houston, now called Johnson Space Center. A hose supplying pressure to his suit became disconnected. The pressure around him fell below 1 pound per square inch. LeBlanc remained conscious for approximately 14 seconds. His final clear memory was feeling moisture on his tongue begin to boil. Technicians started repressurizing the chamber within about 15 seconds, and he regained consciousness as the pressure rose. He recovered without the instant freezing commonly shown in films. His body had retained most of its stored thermal energy throughout the event. A resting person produces close to 100 watts of metabolic heat, roughly comparable to the output of an older incandescent light bulb. The body also emits considerably more energy as infrared radiation. Bare skin near 33 degrees Celsius, facing a very cold background, could radiate several hundred watts across the body's full surface. The net loss would depend on clothing, posture, nearby equipment, and any radiation arriving from surrounding surfaces. Even a loss of several hundred watts would need time to lower the temperature of tens of kilograms of water-rich tissue. The body has substantial thermal mass, meaning it can store a large amount of heat before its core temperature changes by even 1 degree. Evaporation could cool exposed surfaces quickly. The deeper body would respond much more slowly. Pressure loss and oxygen deprivation would therefore dominate the first moments, while whole body freezing would remain a later process. Vacuum creates danger through absence. It removes breathable pressure and leaves almost no material available to distribute heat. Radiation must then carry warmth away photon by photon. That slow escape of energy creates an unusual result on airless worlds. A surface in direct illumination can absorb energy for hours, while nearby ground, hidden in shadow, continues radiating its stored heat into open space. On the Moon, this same absence of air allows heat to remain almost exactly where the light places it. The Moon circles the solar system at nearly the same distance from its star as Earth, so the intensity of incoming sunlight is similar. The difference appears after that energy reaches the ground. Earth's atmosphere absorbs, scatters, and transports heat. Winds carry warm air away from illuminated regions. Clouds reflect part of the incoming light. Oceans store energy and release it slowly. The Moon has no substantial atmosphere to perform any of these tasks. Its surface pressure is so low that the few surrounding atoms scarcely interact with one another. There is no weather and almost no convection. Heat can travel through the ground by conduction, but lunar soil is a poor conductor. This loose surface material is called regolith. It consists of powdered rock, sharp mineral fragments, and small beads of glass created by billions of years of impacts. The grains touch one another at only small points, leaving empty spaces between them. Heat therefore moves through the upper regolith very slowly. Near the lunar equator, one full day from sunrise to the next lasts about 29.5 Earth days. A location remains illuminated for close to 14 Earth days before spending a similar length of time in darkness. During the long daylight period, exposed ground absorbs solar radiation hour after hour. Temperatures near the equator can rise to approximately 127 degrees Celsius. That is hot enough to boil water under ordinary Earth pressure and well beyond the safe operating range of many batteries, plastics, and electronic components. The surface begins cooling as soon as it rotates into darkness. With no warm atmosphere overhead, the ground radiates infrared energy directly into space. By the end of the long lunar night, temperatures can fall toward -173 degrees Celsius. These values describe the surface itself. A few centimeters below the ground, the temperature changes more slowly because the regolith above acts as insulation. Deeper layers retain a more stable average temperature, while the uppermost dust experiences the full cycle of heating and cooling. The exact temperature also depends on the slope of the terrain. A rock face tilted toward incoming sunlight absorbs more energy than flat ground. A surface angled away receives less. Color and mineral composition affect how much light is absorbed, while cracks and boulders cast shadows that can remain far colder than nearby illuminated dust. The strongest examples lie near the lunar poles. Because the moon's axis is tilted by only about 1.5 degrees, sunlight reaches the polar landscape at a very low angle. The rims of some craters receive light for long periods, while their deep interiors remain hidden below the horizon. These permanently shadowed regions may have avoided direct illumination for billions of years. They still receive some energy from scattered light, warm surrounding terrain, and the weak background of space. But the total input is extremely small. NASA's Lunar Reconnaissance Orbiter entered lunar orbit in 2009, carrying an instrument called Diviner. Diviner measured infrared radiation from the surface and allowed scientists to estimate temperatures across the moon. Inside Hermite Crater, close to the North Pole, Diviner recorded temperatures near 25 Kelvin. That is approximately -248 degrees Celsius, colder than the surface of Pluto and only about 22 degrees above absolute zero. The interior of a polar crater is therefore separated from warmer terrain mainly by geometry. Sunlit ground may exist nearby, yet the crater floor cannot see the light source directly. Its view is dominated by dark sky and cold surrounding walls. Energy leaves through radiation, while very little returns. These regions act as cold traps. A water molecule released by a comet impact, carried by the solar wind, or produced through chemical reactions in lunar minerals, may travel across the surface. If it enters a warm area, it can quickly escape again. If it reaches permanent shadow, it may freeze onto a grain of regolith and remain there. Spacecraft observations have found evidence of water, ice, and other volatile compounds in polar soil. Volatiles are substances that readily become gas under warmer conditions. Water, carbon dioxide, ammonia, and several simple carbon-bearing molecules can all be preserved more effectively at extremely low temperatures. The moon is therefore divided into countless local thermal environments. Illumination, slope, depth, surface material, and the amount of visible sky all influence the temperature. A short distance can separate ground hot enough to damage equipment from a shadow cold enough to preserve ice across geological time. A spacecraft carries the same conflict with it. The difference is that its hot and cold regions are connected by metal, wiring, fluids, and shared electrical power, allowing conditions on one side of the vehicle to affect everything inside. A spacecraft carries these neighboring thermal environments wherever it goes. On the International Space Station, the separation between intense heating and deep cooling can move across the structure several times during a single day. The station travels around Earth at roughly 28,000 kilometers per hour. One orbit takes close to 90 minutes, allowing it to circle the planet about 16 times every 24 hours. During each orbit, the station passes through direct sunlight and then enters Earth's shadow. The change happens quickly. Solar arrays and exposed metal structures that were absorbing strong radiation can lose that direct energy within minutes. Later, in the same orbit, they emerge into full illumination again. NASA often gives representative external conditions, ranging from about 121 degrees Celsius on strongly illuminated surfaces to around -157 degrees Celsius in shadow. Those figures describe possible surface environments rather than one temperature shared by the entire station. The actual value depends on the material, its angle toward incoming light, how long it has been illuminated, and whether nearby structures are radiating energy toward it. The station's aluminium truss stretches for more than 100 meters. Solar arrays extend across an even greater width. Different sections can therefore experience very different conditions at the same time. A panel facing Earth may absorb infrared energy from the planet. Another surface may have a clear view of dark sky. Equipment hidden behind a module can remain in shadow, while a nearby antenna receives direct light. Inside the pressurized modules, the thermal problem changes. A typical crew of 6 or 7 people releases several hundred watts of combined metabolic heat while resting. Exercise increases that output. Astronauts regularly spend about 2 hours each day using treadmills, resistance machines, and stationary bicycles to limit the loss of muscle and bone caused by weightlessness. Computers, laboratory equipment, lighting, pumps, communications hardware, and life support machinery produce a much larger continuous heat load. Nearly all the electrical energy used by this equipment eventually becomes thermal energy inside the station. The vacuum outside cannot carry that heat away through moving air. The station must collect it and transport it to specific external surfaces. Within the United States section of the station, water circulates through closed cooling loops. These loops pass through cold plates attached to electronic equipment and through heat exchangers connected to the cabin air system. As the water moves, it absorbs heat from computers, experiments, and other warm components. Water works well inside the pressurized modules because it is safe around the crew and can carry substantial heat. It would create serious problems in the exposed external system, where very low temperatures could freeze it and high temperatures could increase pressure. At the station's outer wall, heat exchangers transfer the collected energy into separate ammonia loops. Ammonia remains useful across a wider range of external operating temperatures and carries heat efficiently through pipes mounted along the station's truss. Mechanical pumps keep the ammonia moving. It travels from the heat exchangers toward large white radiator panels extending into space. The warm fluid passes through narrow channels inside each radiator, and the panels release tens of kilowatts of energy as infrared radiation. The cooled ammonia then returns to collect more heat. This circulation must continue without interruption. A stopped pump can allow equipment temperatures to rise. A leak can reduce the amount of coolant available. Poor radiator orientation can make heat rejection less effective if the panels receive too much direct radiation or face a warm part of Earth. Cold-sensitive hardware creates a separate demand on the same electrical system. Batteries must remain within controlled temperature ranges to charge safely and provide their expected capacity. External valves, fluid lines, cameras, and scientific instruments may carry small resistance heaters. Thermostats activate those heaters when a component approaches its lower operating limit. A shaded instrument can therefore consume power to stay warm, while a computer, only a few meters away, sends heat into the cooling loop. Both systems may be operating during the same passage through Earth's shadow. The International Space Station survives by maintaining this moving balance through every orbit. Its cabin remains comfortable because heat is gathered from some locations, added to others, and released only through surfaces designed for that purpose. The metallic blankets covering much of the station are a major part of that control. Beneath their silver and gold appearance are carefully separated layers that determine how quickly radiation can enter or leave each protected component. Those metallic coverings begin controlling temperature before any pump or heater switches on. The gold-colored material seen on many spacecraft is often aluminized kapton. Kapton is a thin, amber polymer film that remains stable across a wide temperature range. A microscopic aluminium coating reflects much of the radiation striking it, while the amber film beneath gives the blanket its familiar golden appearance. Silver blankets commonly use aluminized mylar, another lightweight plastic film coated with reflective metal. These coverings form multi-layer insulation, usually shortened to MLI. A typical blanket may contain between 10 and 30 reflective sheets. Each sheet can be thinner than ordinary paper. Lightweight netting separates the films, so they do not rest directly against one another. The gaps perform most of the work. Heat cannot cross those spaces through ordinary solid conduction, because very little material connects one layer to the next. Convection is absent inside the evacuated blanket. Radiation remains, but each reflective film returns much of that radiation toward the layer that emitted it. Heat must pass through the blanket gradually, crossing one reflective barrier after another. The result resembles a series of thermal checkpoints. A single shiny sheet offers limited protection. 20 separated sheets can reduce radiative heat transfer dramatically while adding little mass. The separation must remain intact. Compression pushes the films together and creates a direct route for conduction. A tightly fastened corner may leak more heat than a broad section of properly spaced blanket. Wrinkles can bring layers into contact. Stitching, clips, cables, pipes, and mounting bolts also cross the insulation and carry energy through it. Engineers call these paths thermal bridges. The phrase describes any solid connection that allows heat to bypass the intended insulation. A narrow metal bracket can conduct energy far more efficiently than the surrounding blanket, so attachment points are designed and tested carefully. Openings create similar problems. Cameras need clear views. Antennas must transmit signals. Thrusters require exposed nozzles. Electrical wiring and fluid lines must pass between compartments. Every penetration interrupts the insulation and changes the local temperature map. The outermost surface has its own carefully chosen properties. Solar absorptivity describes how much incoming light a material absorbs. Infrared emissivity describes how effectively the same surface releases heat as infrared radiation. These two properties can differ greatly. A white thermal control coating can reflect much of the visible light, reaching it while still emitting infrared energy efficiently. Such a surface remains cooler in strong illumination and can also release internal heat. A polished metal surface may have low infrared emissivity, allowing it to retain warmth more effectively. Spacecraft designers select coatings according to the job of each panel. Radiators need high emissivity. Fuel tanks may benefit from surfaces that limit both absorption and emission. Optical instruments often require stable temperatures and carefully controlled reflections from nearby structures. Passive heat transport can also occur beneath the blankets. Flexible graphite straps or metal braids conduct energy away from warm electronics without using pumps. Heat pipes move larger amounts over greater distances. Inside a heat pipe is a small quantity of working fluid, often ammonia or another fluid chosen for the expected temperature range. Heat entering one end causes part of the liquid to evaporate. The vapor travels through the hollow pipe toward a cooler region where it condenses and releases the energy it carried. A porous lining then draws the liquid back toward the warm end through capillary action. This is the same effect that pulls water through a paper towel. The cycle can continue without a mechanical pump, giving spacecraft a quiet and reliable way to spread heat. Variable conductance heat pipes add a gas reservoir that changes how much of the pipe participates in heat transfer. As temperatures shift, the gas moves and alters the active condensing area. This allows the system to adjust its thermal conductance automatically. Some spacecraft also use thermal louvers. These resemble small shutters placed over a radiating surface. Temperature-sensitive springs open the blades when equipment becomes warm, exposing more area to space. As the system cools, the blades close and reduce heat loss. Small resistance heaters provide local protection where passive control is insufficient. A thermostat monitors a battery, valve, camera, or propellant line. When the temperature falls below a chosen limit, electric current passes through a resistive element and produces heat directly beside the vulnerable component. Together, these systems turn the spacecraft into a carefully arranged thermal map. Blankets slow unwanted exchange. Coatings control how surfaces interact with radiation. Heat pipes spread energy toward safer locations. Louvers and thermostats respond as conditions change. They can slow heat, redirect it, or conserve it for a time. The energy produced by computers, transmitters, motors, and people still remains inside the vehicle until a continuous path carries it toward a surface capable of releasing it. Inside a spacecraft, heat usually begins in places that do not look hot at all. A processor receives electrical power and uses part of it to perform calculations. A radio transmitter converts electricity into a signal. A motor turns a pump or points an antenna. Once that useful work is complete, nearly all the energy ends up as heat somewhere in the vehicle. The warm component may be buried inside an equipment bay, surrounded by insulation and separated from the outer hull. The cold outside cannot reach through those layers and remove the energy on its own. Engineers must build a continuous route from the component to space. That route often begins with a mounting plate made from aluminium or another conductive metal. The electronic unit is bolted tightly against it, so heat can cross through direct contact. A cold plate may sit beneath the assembly. Despite its name, a cold plate is simply a metal panel containing narrow channels through which coolant flows. As the liquid passes through those channels, it absorbs energy from the plate. A pump then carries the warmer coolant through pipes toward a heat exchanger. There, the energy may cross into a separate external loop, chosen to tolerate the temperatures and pressures outside the cabin. The coolant eventually reaches a radiator. A spacecraft radiator is a broad surface designed to release infrared energy efficiently. Its coating has high emissivity, meaning it behaves well as a thermal emitter. The panel must also have a clear view of cold space. A radiator facing a warm planet, an illuminated spacecraft surface, or another radiator receives energy back from those objects and becomes less effective. Engineers describe this geometry with a quantity called the view factor. It represents how much of the radiator's field of view is occupied by another surface. A panel aimed into open sky has a favorable view factor. One partly blocked by the spacecraft may exchange a significant amount of radiation with the vehicle, instead of releasing that energy outward. The amount of heat a radiator can reject depends strongly on its temperature. This relationship is described by the Stefan-Boltzmann law, named after physicists Josef Stefan and Ludwig Boltzmann. The emitted power rises with the fourth power of absolute temperature. The phrase fourth power means that a modest increase in temperature produces a much larger increase in radiated energy. Doubling the absolute temperature raises the ideal radiated power by a factor of 16. At 300 Kelvin, close to 27 degrees Celsius, a perfect blackbody would emit about 460 watts from each square meter. A practical radiator with an emissivity near 9/10 would release a little over 400 watts per square meter when facing a very cold background. A spacecraft producing 1 megawatt of waste heat would therefore need roughly 2,500 square meters of effective radiator area at that temperature. This simplified estimate assumes favorable orientation and does not include blocked views, plumbing losses, aging, or engineering safety margins. 2,500 square meters is comparable to several large houses laid flat beside one another. A more powerful vehicle could require radiators that dominate its shape. Raising the coolant temperature can reduce the required area because hotter panels radiate more strongly. That solution creates new limits. Electronics may need to operate at higher temperatures. Pumps, seals, and coolant must tolerate the added heat. A crewed cabin still has to remain within a comfortable range. Lower temperature systems create the opposite pressure. Sensitive instruments and cryogenic equipment may reject heat through colder radiators, but each square meter releases much less energy. Their panels must become larger or the heat load must be reduced. Radiators also remain exposed. Dust particles and micrometeoroids can strike the panels at several kilometers per second. A punctured coolant channel may leak fluid into space. Designs often divide the radiator into separate sections, so damaged lines can be isolated while the remaining area continues working. Surface coatings gradually change as well. Ultraviolet radiation, charged particles, and contamination from thruster exhaust can alter how a panel absorbs and emits energy. Engineers include performance margins because a radiator near the end of a long mission may behave differently from the clean surface tested before launch. The complete thermal path can stretch across much of the vehicle. Heat leaves a processor, crosses a plate, enters moving coolant, passes through a heat exchanger, and reaches an external panel before finally departing as infrared photons. Every link must remain available. A failed pump can trap energy near the source. A blocked coolant line can leave one compartment warming while the radiator stays cold. Poor orientation can expose the panel to incoming radiation and reduce the final step. The radiator may be perfectly built and fully operational, yet its performance still depends on where the spacecraft points it. A radiator's view of space depends on the attitude of the entire vehicle. In spacecraft operations, attitude means orientation, the direction the vehicle is pointing, and the angle each surface presents to incoming radiation. This became especially important during the Apollo journeys to the Moon. After leaving Earth orbit, the command and service module turned around, docked with the lunar module, and pulled it free from the upper stage of the launch vehicle. The combined spacecraft then spent close to 3 days coasting toward the moon. Holding that docked stack in one fixed position would have exposed the same side to solar heating for many hours. Surfaces on the opposite side would have continued releasing infrared energy toward dark space. The temperature difference would have grown slowly across the vehicle. Apollo crews controlled that difference with a maneuver officially called passive thermal control. Small thruster firings placed the spacecraft into a gentle roll around its long axis at approximately 3 revolutions per hour. One complete rotation, therefore, took about 20 minutes. The crews gave it a more memorable name, the barbecue roll. As the spacecraft turned, each side moved through a repeating cycle of stronger illumination, weaker illumination, and open exposure to space. No surface remained permanently aimed toward the main source of incoming energy. Over time, the rotation distributed heating around the structure and kept average temperatures within a narrower range. The roll was slow enough that the crew barely felt it. Inside the cabin, objects remained weightless, and the moon appeared to drift across the windows. Outside, the changing angle altered the amount of radiation absorbed by the heat shield, windows, antennas, tanks, and metallic skin. Uneven heating can affect a spacecraft, even when no component reaches an immediately destructive temperature. Aluminium expands as it warms. Steel expands by a different amount. Composite materials, wiring, optical mounts, and insulation respond according to their own physical properties. A long structure warmed on one side can bend slightly. A fuel tank can develop warmer and cooler regions that change internal pressure. Antenna supports may shift by a small amount, enough to alter the direction of a narrow communication beam. Optical instruments are especially sensitive because tiny changes in shape can move mirrors or lenses out of alignment. The Apollo stack also carried liquids and gases, whose behavior depended on temperature. Propellants occupied large tanks in the service module. Oxygen and hydrogen were stored for the fuel cells that produced electricity and water. Keeping these systems within predictable ranges helped maintain pressure and ensured that valves and lines behaved as expected. Passive thermal control required regular monitoring. Crews checked the roll rate and used the spacecraft's small reaction control thrusters to correct it when necessary. Venting gases, minor thruster errors, or shifts in the docked configuration could disturb the motion. Modern spacecraft often use reaction wheels for similar pointing work. A reaction wheel is an electrically driven flywheel mounted inside the vehicle. Spinning the wheel faster in one direction causes the spacecraft to rotate slightly in the opposite direction. Several wheels arranged along different axes can point a telescope or maintain a radiator's view without continuously consuming propellant. Thrusters are still needed when the wheels approach their maximum speed or when a larger maneuver is required. A failed wheel or blocked thruster can therefore create thermal consequences as well as navigation problems. The vehicle may lose the orientation that protects sensitive instruments or keeps a radiator clear of warm nearby surfaces. The competing requirements can become precise. Solar arrays need favorable illumination to generate electricity. A communication antenna must face Earth during scheduled contacts. Scientific instruments may need to point toward a planet, star, or distant galaxy. Radiators work best when they face cold sky and avoid direct incoming radiation. Mission planners calculate attitudes that satisfy as many of these needs as possible. Some spacecraft alternate between observation periods and cooling periods. Others limit how long an instrument can point in a particular direction. A maneuver planned for communications may also be timed to protect a battery or prevent one side of the structure from remaining shaded for too long. The quiet rotation of an Apollo spacecraft was therefore part of its thermal control system. Movement distributed energy before large temperature differences could develop. Apollo used rotation to average its exposure. The James Webb Space Telescope would later use an almost perfectly fixed orientation to divide one observatory into two sharply separated thermal worlds. The James Webb Space Telescope uses a carefully preserved orientation to create two thermal environments within one observatory. Webb studies the universe mainly through infrared radiation. This light has wavelengths longer than visible red light and carries information from cool planets, dust clouds, forming stars, and galaxies whose light has traveled across expanding space for more than 13 billion years. Infrared astronomy becomes difficult when the telescope itself is warm. Mirrors, structural supports, detectors, and electronic circuits all emit infrared radiation according to their temperature. A detector may record this local thermal glow alongside the weak signal arriving from a distant galaxy. Electrical activity inside the detector also produces noise, including small, unwanted currents that become weaker as the instrument cools. A cold telescope produces a quieter measurement. Webb operates about 1.5 million kilometers beyond Earth, near the second Sun-Earth Lagrange region. It does not remain motionless at one exact point. The observatory follows a large looping path around that region, while keeping the same general orientation toward its nearby heat sources. Earth, the Moon, and incoming solar radiation remain on one side of the spacecraft. Webb's mirrors and scientific instruments face away from them. A 5-layer sunshield stands between these two sides and creates a permanent artificial shadow. The shield measures roughly 21 meters long and 14 meters wide, giving it an area similar to a tennis court. Each layer is made from extremely thin Kapton film coated with aluminium. Kapton is a durable, amber-colored polymer that remains flexible across a wide range of temperatures. The 5 layers are separated rather than pressed together. This spacing limits direct conduction from one sheet to the next. Radiation striking the first layer is mostly reflected away. The energy absorbed by the film warms it, and the layer releases that heat sideways into space. A smaller amount of energy reaches the second sheet. Each remaining layer repeats the process while receiving less heat than the one before it. Their shapes and spacing guide escaping radiation toward open space instead of allowing it to pass directly through the shield. The warm side can approach about 383 Kelvin, equivalent to roughly 110 degrees Celsius. Only a few meters away, Webb's primary mirror and near-infrared instruments operate near 40 Kelvin, close to minus 233 degrees Celsius. The primary mirror consists of 18 hexagonal segments arranged into a surface 6.5 meters across. Each segment is made from beryllium, a lightweight metal that remains stable at very low temperatures and carries a thin coating of gold, selected for its ability to reflect infrared light. At about 40 Kelvin, the mirrors emit far less infrared radiation than they would near room temperature. This allows the detectors to separate faint astronomical signals from the observatory's own thermal background. Most of Webb reaches its operating temperature passively. The shield blocks incoming energy, while the cold surfaces gradually radiate their remaining heat away. The mid-infrared instrument requires a colder environment. This instrument, commonly called MIRI, observes wavelengths extending to about 28 micrometers. At those longer infrared wavelengths, a detector operating near 40 Kelvin would still generate enough thermal noise to interfere with sensitive observations. MIRI must remain near 7 Kelvin, approximately minus 266 degrees Celsius. A dedicated mechanical cryocooler creates this lower temperature. Compressors on the warmer side circulate helium gas through tubing that crosses the observatory. The system transports heat away from MIRI and eventually releases that energy through hardware on the warm side. The cryocooler consumes electricity and produces waste heat of its own. Webb therefore maintains deep cold through controlled separation. Energy removed from one location must be carried across the spacecraft and released somewhere that will not disturb the instruments. Continuous orientation makes the arrangement possible. Reaction wheels point the telescope during observations, while occasional thruster firings manage the orbit and remove excess momentum from the wheels. Webb can observe only regions of the sky that keep its shield between the cold instruments and the major nearby heat sources. The observatory turns low temperature into scientific precision. Faint infrared signals remain visible because engineers have reduced the competing radiation produced by the telescope itself. Webb can maintain this thermal shadow, while its solar array receives abundant energy near Earth's orbit. A spacecraft traveling much farther outward enters a different balance, where the available sunlight weakens and every electrical watt becomes harder to replace. Near Earth, solar energy is abundant enough to feel almost permanent. A flat surface aimed directly toward incoming sunlight at Earth's average orbital distance receives roughly 1,361 watts of power per square meter. Earth's atmosphere reflects and absorbs part of that energy before it reaches the ground. But a spacecraft outside the atmosphere receives the full flow. Solar cells convert only part of the incoming radiation into electricity. The remaining energy is reflected or becomes heat within the panels. Even with those losses, a moderate array near Earth can operate computers, charge batteries, support communications, and keep temperature control equipment running. This supply weakens rapidly as a spacecraft travels outward. Radiation spreads away from its source across the surface of an expanding sphere. As the sphere grows, the same amount of energy is distributed across a larger area. This produces the inverse square law. At twice Earth's distance, the radiation intensity falls to 1/4. At 3 times the distance, it falls to 1/9. A journey 5 times farther away leaves only 1/25 of the original intensity. Mars orbits at an average distance of about 1.5 times Earth's. A surface there receives close to 590 watts per square meter, around 43% of the value near Earth. Solar-powered spacecraft remain practical at Mars, although their arrays must be larger and carefully managed. Dust makes the problem less predictable. Fine Martian particles can settle on solar panels and reduce their output. During the planet-wide dust storm of 2018, the Opportunity rover received so little sunlight that it could no longer maintain electrical power or internal warmth. Its final communication with Earth occurred on June 10th of that year. At Jupiter, the average solar intensity is only about 50 watts per square meter. This is less than 4% of the energy available near Earth. A panel that produced 1,000 watts in Earth orbit might generate only a few dozen watts there before accounting for temperature, cell efficiency, and radiation damage. NASA's Juno spacecraft demonstrated how far solar power could be extended. Launched in 2011, Juno reached Jupiter in 2016, carrying 3 long solar array wings. Together, they provide close to 60 square meters of collecting area. Near Earth, those arrays could have generated roughly 14 kilowatts. At Jupiter, their output is about 500 watts. The spacecraft must operate its instruments, computer, communications system, and heaters within that much smaller budget. The arrays also add mass and mechanical complexity. Each wing must unfold after launch and remain correctly oriented. Large surfaces can flex during maneuvers, affect the spacecraft's rotation, and become targets for energetic particles trapped in Jupiter's powerful magnetic field. Radiation gradually damages solar cells, reducing the electrical output available later in the mission. Beyond Jupiter, the decline becomes harder to overcome by adding more panel area. At Neptune's average distance, sunlight provides only about 1.5 watts per square meter. That is close to 1/900th of the intensity near Earth. A square meter of panel there receives less solar power than a small household nightlight consumes, even before conversion losses. The reduced energy creates two connected problems. Solar cells produce less electricity, leaving fewer watts for heaters and instruments. The spacecraft also receives less natural warming from sunlight, so shaded components cool more easily. Increasing the size of the arrays eventually becomes impractical. Larger panels require stronger hinges and support structures. They take up more room during launch and create greater pointing demands after deployment. A vehicle traveling toward Uranus, Neptune, or the distant regions beyond them may need enormous arrays simply to operate modest equipment. Many outer system missions therefore carry nuclear power sources. These systems use heat released by radioactive decay, providing electricity and warmth regardless of distance from the solar source. Their output is limited, and it slowly declines with age, but it does not collapse according to the inverse square law. The farther a spacecraft travels, the more its energy system becomes a supply brought from home. Once sunlight can no longer support the heaters, instruments, and transmitter, survival depends on a small reserve of nuclear warmth that is already beginning to fade. That reserve begins inside a ceramic fuel designed to release heat for decades without combustion, moving parts, or any connection to the surrounding environment. The fuel is plutonium-238 dioxide. Plutonium-238 is a radioactive isotope, meaning its atomic nuclei gradually transform into other nuclei. During this process, each nucleus releases an alpha particle. An alpha particle consists of 2 protons and 2 neutrons. It cannot travel far through solid material, so the particles deposit nearly all their energy inside the fuel assembly. Their motion becomes thermal energy, steadily warming the plutonium dioxide. This heat appears continuously. It does not depend on illumination, weather, or a spacecraft's orientation. A probe can travel through a planetary shadow or continue far beyond the practical range of solar arrays while the fuel remains warm. The plutonium is formed into a ceramic rather than stored as loose metal. Ceramic plutonium dioxide has a very high melting temperature and tends to break into larger pieces instead of producing fine airborne material during an accident. Individual fuel units are protected by iridium cladding and surrounded by graphite structures designed to resist impact and re-entry heating. The heat alone can keep nearby components warm, but a spacecraft also needs electricity. A radioisotope thermoelectric generator converts part of the thermal output into electrical power. Thermoelectric materials produce voltage when one side is kept hotter than the other. This process is called the Seebeck effect, named after Thomas Johann Seebeck, who observed the phenomenon in the early 19th century. Inside the generator, thermocouples sit between the hot plutonium fuel and colder exterior fins. A thermocouple is a pair of connected materials that responds to a temperature difference by driving an electric current. The fuel maintains the hot side, while the fins radiate energy into space and preserve the cooler side. Traditional radioisotope generators convert less than 10% of their heat into electricity. A unit may release several thousand watts of thermal power, while producing only a few hundred watts of electrical power. That apparent inefficiency can still be useful aboard a cold spacecraft. Some of the remaining thermal energy travels through structural connections into the vehicle, reducing the electrical power required by heaters. Designers can place equipment near the generator or add conductive paths that guide warmth towards selected compartments. Voyager 1 and Voyager 2 each launched in 1977, with 3 radioisotope thermoelectric generators mounted on a boom away from their scientific instruments. At launch, each spacecraft received roughly 470 watts of electrical power from the combined generators. The greater thermal output also helped protect systems during their journeys through the outer solar system. Newer vehicles use updated designs. NASA's Curiosity rover landed on Mars in 2012 with a multi-mission radioisotope thermoelectric generator. Perseverance arrived in 2021, carrying the same general type of unit. Each generator produced around 110 watts of electricity near the beginning of its mission, while releasing much more energy as heat. That warmth is valuable during the Martian night, when surface temperatures can fall far below freezing. Coolant lines carry heat from the generator through the rover, helping keep batteries, electronics, and scientific instruments within their operating ranges. Smaller devices, called radioisotope heater units, can protect individual components without generating electricity. A typical unit contains a small amount of plutonium, 238, and produces about 1 watt of continuous thermal power. Spacecraft have used them beside cameras, batteries, motors, and delicate mechanisms that would otherwise require electrical heaters. The energy source lasts for decades because plutonium-238 has a half-life of approximately 87.7 years. After one half-life, half of the original radioactive nuclei remain. The heat output therefore declines gradually, rather than ending suddenly. Electrical production falls somewhat faster. The radioactive fuel weakens as expected, while thermoelectric materials also lose performance after years of exposure to high temperature and radiation. Electrical connections age, and the temperature difference across the generator can change. From the moment a spacecraft leaves Earth, its nuclear power budget is already shrinking. The decline may be slow enough to support instruments across half a century, yet it never pauses. Eventually, the remaining electricity can no longer operate every heater, transmitter, and scientific instrument together. The spacecraft must begin choosing which systems will stay alive. Voyager 1 and Voyager 2 began their journeys in 1977, with more electrical power than their original planetary missions required. Each spacecraft carried 3 radioisotope thermoelectric generators, together producing roughly 470 watts at launch. That was enough to run 10 scientific instruments, maintain the spacecraft's computers, operate its radio, and keep vulnerable equipment warm while the probes crossed the outer solar system. Their power systems also released thousands of watts as heat, much of which escaped through the generator's radiator fins, while smaller amounts warmed the spacecraft through structural connections. Nearly half a century later, the same plutonium is still decaying. The thermocouples converting its heat into electricity have also aged. Together, these changes remove about 4 watts of electrical capacity from each spacecraft every year. 4 watts would barely illuminate a small modern lamp. On Voyager, it can represent the difference between keeping a heater active and preserving enough voltage for a scientific instrument. The annual loss accumulates, so survival has become a controlled process of subtraction. Systems no longer needed after the planetary encounters were shut down first. The cameras stopped operating decades ago. Instrument heaters followed when engineers concluded that selected equipment might continue working below its original tested temperature. Several instruments did exactly that, returning data while colder than their qualification limits. The remaining choices have become more difficult. Attitude control must keep the high-gain antenna aimed toward Earth. The flight computer must continue processing commands and protecting the spacecraft. Radio equipment must transmit a signal across more than 20 billion kilometers. These basic functions compete with scientific instruments and heaters for the same diminishing supply. In October 2024, engineers commanded a heater on Voyager 1 to turn on. The resulting power demand triggered the spacecraft's fault protection system, which switched off its usual transmitter and activated a lower power backup. Restoring normal communication required commands that took almost 23 hours to reach the probe, followed by another long wait for its response. A planned roll maneuver on February 27, 2026, produced another unexpected power decrease. With very little voltage margin remaining, engineers decided to remove a larger electrical load before the spacecraft's automatic protection system made the decision for them. On April 17, 2026, Voyager 1's low-energy charged particles experiment was switched off. The instrument had operated for almost 49 years, measuring ions, electrons, and cosmic rays through the outer solar system and into interstellar space. Voyager 1 continued with two active science instruments, its magnetometer and plasma wave system. Every shutdown changes the thermal balance. An instrument consuming electricity also releases heat. Turning it off saves power, yet it can make the surrounding compartment colder. Engineers must consider whether saved watts disappear from the spacecraft's thermal map and whether another component depended on that waste heat. The hydrazine propellant used by Voyager's small pointing thrusters freezes at around 1.5 degrees Celsius. NASA thermal studies have tracked temperatures along the narrow propellant lines because losing liquid flow could prevent the thrusters from keeping the antenna aligned with Earth. Insulation slows the cooling. Dedicated heaters protect selected locations, while warmth from operating electronics spreads through the aluminium structure. Engineers can sometimes shift electrical loads to place more waste heat near a vulnerable line. Each adjustment must preserve enough power for communication and control. The mission has no guaranteed final date. Careful reductions may allow some science to continue into the next decade, while an unexpected failure could end useful operations earlier. Voyager is surviving through permanent choices made a few watts at a time. Useful operations could end while most of the spacecraft remains above freezing. A single critical line, valve, material, or circuit reaching its thermal limit would be enough. A spacecraft component reaching its lower temperature limit rarely fails in the dramatic way shown in fiction. Metal does not simply become glass-like and shatter throughout the vehicle. Cold changes each material according to its composition, internal structure, manufacturing history, and the way it is connected to neighboring parts. Engineers describe dimensional change with the coefficient of thermal expansion. This value shows how much a material expands when warmed or contracts when cooled. Aluminium, steel, glass, solder, adhesives, circuit boards, and carbon fiber composites all have different coefficients. A metal housing may shrink more than the glass lens mounted inside it. Copper wiring can contract at a different rate from the circuit board supporting it. Adhesive joining two surfaces may be pulled in opposing directions. Each individual change can be tiny, yet repeated cooling cycles concentrate stress along seams, solder joints, connectors, and mounting points. A long aluminium structure cooled by 100 degrees can shorten by several millimeters. If a steel brace attached to it contracts less, the connection between them must absorb the difference. Bolts can loosen or carry unexpected loads. Optical elements can shift far enough to affect alignment even when every part remains intact. Mechanical strength also changes with temperature. Some steels with a body-centered cubic crystal structure can undergo a ductile to brittle transition. Ductile material can bend and deform before breaking. Below its transition range, the same steel may absorb less energy before a crack spreads. The transition temperature depends on the alloy, heat treatment, grain structure, and any flaws left during manufacturing. Austenitic stainless steels, which have a different crystal arrangement, often retain useful toughness at cryogenic temperatures. Selected aluminium alloys can also perform well in extremely cold tanks and spacecraft structures. Material choice, therefore, matters more than a general rule about metal becoming brittle. Moving mechanisms face another set of limits. Lubricants usually become more viscous as temperature falls. Viscosity describes resistance to flowing. A grease that moves easily at room temperature may thicken enough to slow a motor, prevent a bearing from turning freely, or increase the electrical power needed to move an antenna. Liquid lubricants can evaporate in vacuum, so spacecraft often use specially formulated oils, greases, or dry coatings. Poorly protected metal surfaces may also cold weld when they touch in vacuum. Cold welding occurs when clean metal surfaces bond together, because no layer of air or oxide separates them. Surface coatings and carefully selected material pairs reduce that risk. Elastomer seals behave differently again. Elastomers are flexible rubber-like materials used around valves, doors, and fluid connections. As they cool toward their glass transition temperature, their molecular chains lose mobility. The seal hardens, bends less easily, and may recover slowly after compression. A valve can still move, while the seal around it no longer follows the surface closely enough to prevent leakage. Electrical systems remain vulnerable even without moving parts. Batteries deliver less available capacity at low temperature because their chemical reactions slow. Internal resistance rises, causing more voltage to be lost inside the cell. Charging a cold lithium-ion battery can create an additional hazard called lithium plating. Instead of moving safely into the graphite electrode, metallic lithium can collect on its surface. This reduces capacity and may damage the internal separator. Spacecraft battery heaters often bring cells into an approved temperature range before charging begins. Capacitors can change value as their dielectric materials cool. Sensors may report slightly different readings. Quartz crystal oscillators, which provide precise timing signals, drift in frequency as temperature changes. Computers and radios depend on that timing, so oscillator temperature is often controlled or its predictable drift is corrected electronically. Fluids create firm boundaries because they can change phase. Hydrazine, used in many spacecraft thrusters, freezes near 1.4 degrees Celsius. A frozen section inside a narrow propellant line can block flow and remove attitude control even while the main tank remains liquid. Water creates mechanical stress because it expands as it freezes. Ice forming inside a sealed pipe can press against the walls, joints, and valves. Later thawing may restore flow while revealing cracks created during the frozen period. Other coolants and propellants have their own freezing points, viscosity changes, and pressure behavior. A spacecraft therefore contains thousands of overlapping temperature requirements. Most remain manageable when treated separately. Their interfaces create the greatest difficulty because materials contract differently, fluids pass through solid structures, and electrical systems depend on mechanical alignment. Once one limit is crossed, the effects can spread through shared power circuits, coolant paths, structural supports, and pointing systems. These limits become more dangerous when a spacecraft loses the ability to control its position. In May of 2009, NASA's Spirit rover became embedded in unusually soft soil near the western edge of a shallow Martian feature called home plate. Its wheels churned through loose material beneath a thin crust, leaving the rover tilted and unable to drive onto firmer ground. The loss of movement affected more than exploration. Spirit relied on solar arrays for electricity, and engineers normally positioned the rover to collect as much winter sunlight as possible. Its trapped wheels prevented them from achieving the most favorable angle. Dust had already accumulated across the arrays. As the Martian season changed, the solar source remained lower in the sky and daylight weakened. Spirit entered its fourth Martian winter with less electrical energy available each day. Some of that energy had to operate heaters. Spirit also carried small radioisotope heater units that released continuous warmth through plutonium decay, but their output was limited. They could protect selected locations, while the rover's electronics and batteries still depended heavily on electrical heating and waste heat from active systems. Engineers prepared Spirit for a low-power state. Instruments were shut down, communication schedules were reduced, and energy was conserved for the computer and thermal protection. Internal temperatures were still expected to fall below levels the rover had experienced during earlier winters. Spirit sent its final transmission on March 22, 2010. NASA continued listening and sending commands for more than a year, but no further signal arrived. Excessive winter cold remains a leading explanation for the permanent loss. The sequence began with soil beneath a wheel. That mechanical problem changed the rover's orientation. The new angle reduced electrical generation, which weakened its ability to heat itself. Colder batteries then offered less usable capacity, leaving even less energy for recovery. Similar coupling appears aboard Voyager. The spacecraft distributes electricity through a shared power bus. A bus is the main electrical pathway supplying several systems from the same source. Automatic fault protection logic monitors its voltage and responds when the available margin becomes too small. A heater, drawing a few unexpected watts, can pull the voltage downward. The protection system may respond by shutting off equipment, switching transmitters, or placing the spacecraft in a safer operating mode. Those actions alter the amount and location of heat being produced. Turning off an instrument removes its electrical load and also removes its waste heat. A nearby propellant line or electronic assembly may then cool faster than engineers predicted from the electrical saving alone. The effects can continue through systems that appear unrelated. A colder battery delivers less power. Reduced power limits heater use. Hydrazine approaching its freezing point may stop flowing through a narrow line. Without reliable propellant flow, attitude control thrusters may lose the ability to point the vehicle precisely. A pointing error can direct a radiator toward a warmer surface or move a communication antenna away from Earth. Solar-powered vehicles can also expose their arrays at an unfavorable angle, reducing the energy available to correct the original problem. Spacecraft designers search for these connections long before launch. Full vehicles and individual components are placed inside thermal vacuum chambers, where pumps remove the air and cold walls imitate the radiative environment of space. Powerful lamps reproduce solar heating from selected directions. Thousands of sensors may be attached to tanks, circuit boards, structural joints, batteries, and coolant lines. Engineers operate instruments, cycle heaters, and test different orientations while watching how temperatures spread through the vehicle. The tests reveal unexpected paths. A cable bundle may conduct heat around insulation. A mounting bracket can cool an electronic box faster than a computer model predicted. Switching on one instrument may warm a nearby battery enough to change its charging behavior. No ground test can reproduce every combination created by years of aging, dust, radiation exposure, and declining power. Engineers therefore preserve margins and build automatic responses into the vehicle. A robotic mission can survive by surrendering scientific capability. A crewed habitat has fewer disposable systems because its pumps, air processors, water equipment, and temperature controls are part of the environment keeping its occupants alive. Inside a crewed spacecraft, every person becomes part of the thermal control system. A resting human body releases roughly 80 to 120 watts of heat. That energy comes from metabolism, the chemical process that converts food and oxygen into motion, tissue repair, electrical activity in the nervous system, and warmth. During exercise, the output can rise to several hundred watts. On the International Space Station, astronauts often exercise for about 2 hours per day to reduce muscle and bone loss. A crew member working hard on a treadmill or resistance machine can briefly produce several times the heat released while sleeping. Across a crew of 6 or 7 people, resting metabolic heat alone can approach the output of several household space heaters running at low power. A larger habitat carrying dozens or hundreds of people would generate a continuous biological heat load measured in kilowatts. Human bodies also release water. Moisture leaves through breathing and perspiration, even when no sweat is visible. In a sealed cabin, that vapor remains inside until equipment removes it. Air behaves differently in microgravity. On Earth, warm air becomes less dense and rises, while cooler air sinks. This buoyancy-driven convection helps mix rooms naturally. In orbit, the difference in density produces almost no useful upward movement because there is no stable up or down. A warm pocket of air can remain close to a person's face. Exhaled carbon dioxide can collect around a sleeping astronaut if ventilation is poor. Fans therefore operate continuously near bunks, workstations, exercise equipment, and laboratory racks. The moving air carries heat and moisture toward the environmental control system. It passes across a condensing heat exchanger, a cold surface that removes both. Water vapor cools until it changes into liquid droplets, much like moisture forming on a cold window. The collected water enters the habitat's recovery system. On the station, water from cabin humidity is processed along with wastewater from other sources. Filters and treatment equipment return much of it to a condition suitable for reuse. Removing moisture also controls humidity. Air that becomes too dry can irritate eyes and airways. Excess humidity encourages condensation inside walls, electrical connectors, and hidden spaces where liquid water can damage equipment or support microbial growth. Carbon dioxide must be removed at the same time. Each person exhales it continuously as a product of metabolism. Scrubbers pull the gas from cabin air using materials or chemical systems that capture carbon dioxide while allowing oxygen and nitrogen to continue circulating. These systems generate heat of their own. Fans contain electric motors. Pumps move water through pipes. Carbon dioxide removal equipment consumes power. And some capture materials must be heated during regeneration, so they can release the gas and be used again. Lighting, computers, communication equipment, food preparation, medical devices, and waste processing add further thermal loads. Exercise machines turn muscular effort into friction and electrical energy, which eventually becomes heat inside the cabin. Agriculture would increase the total in a large interplanetary habitat. Plants need lamps when natural light is unavailable or poorly directed. Pumps circulate nutrient-rich water. Fans move air through leaves, and temperature control keeps roots and growing chambers within suitable ranges. Nearly all the electrical energy entering those systems ends as heat. The crew's core temperature must remain close to 37 degrees Celsius. Even modest departures can impair judgment, coordination, sleep, and physical performance. The cabin therefore needs a stable temperature, while humidity, airflow, and carbon dioxide remain within narrow limits. Maintaining that environment requires continuous movement of energy. Cabin air transfers warmth into heat exchangers. Coolant carries it through the habitat. Pumps move the fluid toward radiators, where the energy can finally leave as infrared radiation. In a large spacecraft, electronic and life support equipment can produce far more heat than the people themselves. Yet the crew remains inseparable from the system. Their food becomes metabolic energy. Their breathing adds moisture and carbon dioxide. Their movement changes airflow and heat production. The habitat functions as a heat engine built around living bodies. As its population and machinery grow, the radiators required to protect that life can become some of the largest structures on the entire spacecraft. A large habitat turns every ordinary activity into part of its thermal budget. Lighting supports living areas and crop chambers. Pumps move water through recycling systems. Computers manage navigation, communications, and environmental control. Workshops refine materials and manufacture replacement parts. Medical equipment, kitchens, exercise spaces, and propulsion support systems all draw electrical power. After that electricity performs useful work, nearly all of it becomes heat somewhere inside the vehicle. A motor may turn a pump, but friction and electrical resistance eventually warm the motor and the moving fluid. A lamp produces useful light, yet the light is later absorbed by walls, plants, equipment, or human bodies and converted into thermal energy. A computer may perform billions of calculations before its electrical input reaches the cooling system as heat. 1 megawatt represents 1 million joules of energy every second. A habitat consuming 1 megawatt continuously must eventually release nearly that same amount of power into space if its internal temperature is to remain stable. At roughly 300 Kelvin, close to 27 degrees Celsius, a practical high-emissivity radiator might release about 400 watts from each square meter when it has a clear view of cold sky. Under simplified conditions, rejecting 1 megawatt would require around 2,500 square meters of effective emitting area. That is approximately half the area of an American football field, spread across thin panels connected to pumps, fluid lines, and structural supports. A 10 megawatt habitat operating at a similar radiator temperature could require about 25,000 square meters. Agriculture, manufacturing, large computing systems, and hundreds or thousands of inhabitants could raise the load much further. Electric propulsion systems and nuclear reactors may add their own cooling loops, sometimes operating at temperatures very different from the cabin. The Stefan-Boltzmann relationship makes radiator temperature one of the most powerful design choices. Because emitted power rises with the fourth power of absolute temperature, a hotter panel can release much more heat from the same area. This allows engineers to reduce radiator size by circulating hotter coolant. The rest of the spacecraft must then tolerate those higher temperatures. Pumps and seals need suitable materials. Electronics may require separate lower temperature loops. Human living spaces still need to remain near comfortable conditions. Large vehicles may therefore use several thermal circuits. A high-temperature loop can serve a reactor or industrial process. Cooler loops can protect computers, food stores, medical equipment, and crew cabins. Heat exchangers keep these systems connected while preserving their different operating ranges. Lower radiator temperatures create broad surfaces. Higher temperatures place greater demands on materials and insulation. Every choice moves the difficulty somewhere else within the ship. The radiators themselves must remain open to space. Thick shielding would block the infrared radiation they are meant to release. Their useful form is broad, lightweight, and relatively thin, which makes them among the most exposed structures on the vehicle. Micrometeoroids can puncture coolant channels. Temperature differences can warp panels and place stress on joints. A failed hinge may prevent a folded radiator from deploying after launch. Dust, radiation, and contamination can slowly change a surface coating and reduce its ability to emit heat. Large systems can divide the radiators into independent sections. Isolation valves close around a damaged channel, while coolant is redirected through the remaining panels. Multiple pumps and separate loops allow part of the system to continue operating after a leak or mechanical failure. Redundancy adds pipes, valves, structure, and mass. The need for protection grows at the same time that the radiator must stay exposed. A compact habitat can place thick shielding around its crew and machinery, while its thermal surfaces extend far beyond that protected volume. The result may look unlike the solid vessels usually imagined in fiction. A generation ship could be dominated by long wings, rotating panels, or broad sheets arranged around a smaller shielded core. From a distance, the living compartments might appear secondary to the surfaces releasing their heat. Its infrared glow would reveal how much power the habitat was using, even if no visible light escaped. A traveling civilization would carry its energy consumption across space as a measurable thermal signature. Those vast panels could be rejecting comfortable cabin heat, while nearby tanks and transfer lines remain at cryogenic temperatures. The same vehicle may need kilometers of warm radiator plumbing beside reservoirs holding fuel cold enough to freeze nearly every familiar substance. A large spacecraft may need to keep neighboring systems separated by hundreds of degrees. Hydrazine has been used for decades in attitude control thrusters because it can remain liquid for long periods and ignites reliably when passed over a catalyst. Its freezing point is close to 1.4 degrees Celsius, which places it only slightly below the temperature of an ordinary refrigerator. A spacecraft cabin may remain near room temperature, while exposed hydrazine lines run through colder structural areas. Small resistance heaters are often wrapped around pipes, valves, and thruster assemblies to preserve liquid flow. Insulation slows heat loss, while thermostats activate the heaters before the propellant approaches its freezing point. Future propulsion systems may require the opposite treatment. Liquid oxygen boils near 90 Kelvin at standard pressure, equivalent to roughly -183 degrees Celsius. Liquid hydrogen boils near 20 Kelvin, close to -253 degrees Celsius. A tank holding either substance must remain far colder than the crew cabin, its computers, and most structural materials. Liquid hydrogen creates the greater challenge because even a small heat leak matters near 20 Kelvin. Energy can enter through the tank supports that hold it inside the vehicle. Pipes, wiring, valves, sensors, and mounting hardware form additional conductive paths. Each solid connection becomes a thermal bridge between the cold tank and the warmer spacecraft. Multi-layer insulation surrounds many cryogenic tanks. Thin reflective films separated by mesh reduce radiative heating, much as spacecraft blankets protect electronic equipment. Tank penetrations remain unavoidable. Propellant must enter and leave through pipes. Sensors must report temperature and pressure. Structural supports must restrain tons of liquid during acceleration. Heat crossing those paths raises the energy of the propellant. Some liquid then changes into gas. This process is called boil-off. As vapor collects above the liquid, tank pressure rises. Engineers can vent part of the gas into space to keep the pressure within safe limits. Every vented molecule represents fuel that can no longer be used for propulsion. Boil-off may be manageable during a short launch campaign or a journey lasting several days. It becomes costly during missions lasting months or years. A vehicle arriving at its destination with only part of its original hydrogen has lost both propellant and the performance expected from carrying it. Tank pressure can also be managed by mixing the fluid. In weightlessness, liquid may collect in uneven layers, while warmer vapor occupies other regions. Pumps, or small jets, circulate the contents, reducing local hotspots and bringing warmer liquid toward a cooling surface. Zero boil-off systems aim to preserve the full propellant supply. A cryocooler removes heat from the tank as quickly as it enters. Vapor can be cooled until it condenses back into liquid, keeping pressure under control without continuous venting. NASA has tested zero boil-off tank concepts using cryogenic fluids, multi-layer insulation, active cooling, and internal mixing. Related reduced boil-off systems allow a small controlled loss while using less electrical power and lighter equipment. The name cryocooler describes a refrigerator designed for extremely low temperatures. Compressors and heat exchangers move energy away from the cold tank. The machinery consumes electricity and adds mass to the spacecraft. Pumps, valves, and moving parts also create additional failure points. Refrigeration shifts heat rather than destroying it. Energy removed from liquid hydrogen travels through the cryocooler and enters a warmer cooling loop. The electrical power used by the machinery becomes heat as well. Both loads must eventually reach an external radiator. This creates an unusual thermal arrangement. A crew may live near 20 degrees Celsius. Hydrazine lines may require heaters to stay above 1.4 degrees. Liquid oxygen tanks remain near 90 Kelvin, while hydrogen storage approaches 20 Kelvin. Radiators connected to the habitat may operate hundreds of degrees warmer than the coldest propellant. Each region depends on the others. Reactor power runs the cryocoolers. The cryocoolers protect the fuel. Radiators release the transferred energy. Insulation and structural design limit how quickly warmth leaks back toward the tanks. The spacecraft becomes a collection of climates, joined by carefully controlled paths. Its coldest reservoir can sit meters from living people and operating machinery. Beyond the hull, the few particles drifting through space may carry enough individual energy for physicists to assign them temperatures of thousands or even millions of degrees. The particles outside the spacecraft can carry far more energy than their surroundings seem to suggest. Interstellar space contains several overlapping forms of gas. Some regions hold mostly neutral atoms, while others contain plasma, a gas in which electrons have separated from atomic nuclei. Scientists describe these regions partly by temperature, but that number refers to the average kinetic energy of the particles. Kinetic energy is the energy of motion. The warm, interstellar medium often measures between roughly 6,000 and 10,000 Kelvin. Hot ionized regions can approach 1 million Kelvin, especially where supernova explosions and powerful stellar winds have heated the gas. A spacecraft passing through 1 million Kelvin plasma does not experience anything resembling a million Kelvin furnace. The missing ingredient is density. Warm regions of the interstellar medium may contain only a fraction of one atom in each cubic centimeter. In the hot ionized phase, the density can fall toward 1,000th of a particle per cubic centimeter. A cube 10 centimeters across could therefore contain only about one particle. Air at sea level contains roughly 10 to the 19th power particles in each cubic centimeter. Those particles collide constantly with skin, clothing, buildings, and machinery. Their enormous number allows terrestrial air to deliver or remove heat quickly. Interstellar particles travel long distances between collisions. Physicists call the average distance between collisions the mean free path. In an extremely thin plasma, that path can stretch across astronomical distances, depending on the particle energy and the surrounding magnetic field. A fast-moving proton striking a spacecraft transfers some energy. The next collision may arrive only after the vehicle has traveled through a vast volume of almost empty space. The total heat delivered each second remains extremely small because so few particles reach the surface. This separates several quantities that everyday language often combines. Temperature describes the average energy carried by each particle. Thermal energy density measures how much particle energy exists within a given volume. Heat capacity describes how much energy a material can store as its temperature changes. Heat flux measures how rapidly energy crosses a surface. A plasma can have a very high temperature while possessing a low thermal energy density and delivering almost no useful heat flux. Each particle is energetic, but there are too few of them to warm a large object. The solar wind provides a nearby example. Around Earth, its protons and electrons may be assigned temperatures of tens or hundreds of thousands of Kelvin. Spacecraft still need heaters because the solar wind is far too thin to keep their components warm. The solar corona is even hotter, reaching more than 1 million Kelvin in many regions. A probe traveling through it receives heating from several sources, including particle impacts and intense radiation. Engineers calculate each contribution separately because the plasma temperature alone cannot describe the load. The same separation applies between the stars. Particle bombardment adds a small amount of energy to the spacecraft. Starlight and distant infrared sources provide radiative heating. The cosmic microwave background continues arriving from every direction with a temperature near 2.725 Kelvin. Electronics, reactors, people, and pumps add energy from inside. Each source follows its own physical pathway. A thermometer exposed in interstellar space would respond to the radiation it absorbs, the particles that strike it, and any heat stored within its material. It would not automatically display the temperature assigned to the surrounding plasma. Its final reading would emerge from the balance among all incoming and outgoing energy. This is why a single phrase, such as the temperature of space, becomes increasingly incomplete. One location can contain million Kelvin ions, microwave radiation near absolute zero, and a spacecraft maintained near room temperature. These conditions coexist because they describe different populations of energy interacting at very different rates. Even the faint cosmic background does not form an absolute lower boundary for every natural object. Under unusual conditions, expanding gas can lose energy faster than that ancient radiation restores it, producing a region colder than the background filling the universe. The opposite thermal process appears in a cloud of gas surrounding a dying star about 5,000 light-years from Earth. This object is called the Boomerang Nebula. It lies in the southern constellation Centaurus and contains material expelled during a late stage in the life of its central star. The star has exhausted much of the fuel that supported its earlier stability and is shedding its outer layers into space. Some of that gas is moving outward at extraordinary speed. The fastest portions of the flow travel at roughly 160 kilometers per second. At that rate, the gas could cross the distance between Earth and the Moon in about 40 minutes. Observations of molecules within the outflow revealed temperatures near 1 Kelvin. That is approximately minus 272 degrees Celsius, leaving the gas only about 1 degree above absolute zero. The Boomerang Nebula is therefore colder than the cosmic microwave background surrounding it. This can happen because temperature describes the random microscopic motion of particles, while the entire cloud is also undergoing large-scale outward motion. As the gas expands, it pushes against the material around it and spreads into a larger volume. Energy that once supported random molecular motion is converted into the organized expansion of the cloud. Physicists call this adiabatic cooling. An adiabatic process occurs when a gas changes temperature mainly through expansion or compression, without receiving enough outside heat to cancel that change. A familiar version occurs when compressed gas escapes from an aerosol can. The expanding gas cools, and the container may become cold to the touch. The Boomerang Nebula follows the same underlying principle on an astronomical scale, with a rapidly expanding flow produced by a dying star. The cooling has been unusually effective because the mass loss is both fast and dense. Gas expelled earlier formed a surrounding envelope. Newer material then expanded through that environment, performing work as it pushed outward. The random kinetic energy of the molecules fell until parts of the flow reached temperatures below the background radiation field. Astronomers identified this extreme cold by studying how the nebula affected microwave radiation passing through it. Molecules in the gas absorbed some of the cosmic background photons, creating a detectable signature. The cloud appeared colder than the radiation behind it because it removed energy from that background along the line of sight. The state cannot remain unchanged forever. Cosmic microwave photons continue entering the cloud from every direction. Nearby stars also supply small amounts of radiation. Dust grains absorb energy and exchange it with surrounding gas. As the expansion slows and the density falls, these outside sources will gradually become more important. The nebula will eventually warm toward a new equilibrium. Its present temperature records a temporary period when expansion removed internal energy faster than the surrounding universe could replace it. The Boomerang Nebula is often described as the coldest known large natural environment. The word large matters because laboratories on Earth have produced temperatures far lower. Physicists can cool small groups of atoms into the nanokelvin range, meaning billionths of a Kelvin above absolute zero. More specialized experiments have reached effective temperatures measured in picokelvin, or trillionths of a Kelvin. These laboratory systems may contain only a tiny cloud of atoms held inside magnetic or optical traps. Lasers slow the particles, while carefully controlled fields isolate them from the warmer room and equipment around them. The experiment requires continuous preparation and lasts for a limited time. The Boomerang Nebula extends across an enormous volume and contains matter expelled naturally by a star. No laboratory refrigeration system created it. Its cold emerged from motion, pressure, and expansion operating across space. At temperatures close to 1 Kelvin, molecular movement becomes extremely slow. Collisions occur less often. Many reactions lose the energy needed to proceed, and substances remain frozen on dust grains for long periods. Chemistry continues within that cold. Its pathways become quieter, slower, and strongly shaped by radiation arriving from the surrounding galaxy. Inside a dense molecular cloud, temperatures can fall toward 10 Kelvin, only about 10 degrees above absolute zero. These clouds contain more material than the thin gas between ordinary stars, yet they remain an excellent vacuum by terrestrial standards. Their dust absorbs much of the visible and ultraviolet radiation arriving from outside, leaving the interior dark, cold, and chemically sheltered. The dust grains are extremely small, often comparable to particles in smoke or fine powder. Many are made from silicate minerals or carbon-rich material. At 10 Kelvin, gas molecules striking these grains can remain attached instead of immediately returning to space. Over time, each grain develops an icy mantle. Water forms a large part of this coating. Carbon monoxide and carbon dioxide freeze beside it. Methane, ammonia, and methanol also accumulate when local conditions allow. The mantle may contain many layers, built molecule by molecule during thousands or millions of years inside the cloud. These surfaces change how chemistry proceeds. In open interstellar gas, atoms and molecules are separated by enormous distances. Even inside a dense cloud, collisions remain uncommon compared with those in Earth's atmosphere. A dust grain collects particles from the surrounding gas and holds them within a microscopic area, increasing the chance that they will meet. Hydrogen is especially important. Individual hydrogen atoms can land on an icy surface and move between weak attachment sites. When two meet, they can combine into molecular hydrogen. Other hydrogen atoms react with carbon monoxide, oxygen-bearing compounds, and fragments of larger molecules. This gradual addition of hydrogen is called hydrogenation. A sequence of hydrogenation reactions can transform simple carbon monoxide into more complex substances, including formaldehyde and methanol. Methanol is one of the most abundant complex molecules found in interstellar ice. At such low temperatures, many reactions appear to lack enough energy to begin. A chemical reaction often requires particles to cross an energy barrier before new bonds can form. Hydrogen can sometimes cross this barrier through quantum tunneling. Quantum tunneling is a property of very small particles. Instead of climbing over the full energy barrier in the ordinary way, a particle has a small probability of appearing on the other side. Hydrogen is light enough for this effect to matter in cold interstellar chemistry. The reaction may remain slow, but molecular clouds can persist for immense spans of time. A process occurring rarely on one grain can become important when repeated across trillions of grains for hundreds of thousands of years. The cloud is also exposed to energetic radiation. Cosmic rays penetrate deeply into regions that ordinary starlight cannot reach. When they strike gas or dust, they can break molecules apart and produce energetic fragments. Ultraviolet photons are created within the cloud when cosmic rays interact with hydrogen. These photons strike the frozen mantles, rearranging atoms and opening new reaction pathways. Laboratory experiments using cold ices and ultraviolet lamps have produced increasingly complex carbon-bearing compounds through similar processing. Radio telescopes have detected complex organic molecules inside interstellar clouds. In chemistry, organic simply means that the molecule contains carbon arranged with elements such as hydrogen, oxygen, or nitrogen. The term does not prove that life is present. It shows that cosmic environments can assemble complicated chemical structures before planets have formed. Gravity eventually changes the setting. Dense regions within a molecular cloud can collapse and form new stars. Material surrounding each young star flattens into a rotating protoplanetary disk where dust grains collide and begin building larger objects. Some of the earlier ice chemistry survives this process. It can become trapped inside comets and asteroids, forming in the cold outer regions of the new system. These bodies may preserve primitive material for roughly 4.5 billion years. The European Space Agency's Rosetta mission found evidence of this preservation around Comet 67P. Its instruments detected glycine, an amino acid used by life on Earth to build proteins. Rosetta also detected phosphorus-bearing material, providing another element important to terrestrial biology. The comet carried these substances without showing that life had formed there. Its frozen material demonstrated that chemically useful ingredients can survive from the early history of a planetary system. Cold, therefore, performs two related jobs within molecular clouds. It preserves fragile substances and holds reactants together on dust grains long enough for unusual chemistry to proceed. The same low temperatures that threaten spacecraft can help prepare material later incorporated into planets, oceans, and atmospheres. These frozen molecules can endure for billions of years, while the radiation surrounding them continues to stretch and cool as the universe expands. The radiation surrounding those ancient molecules has been losing energy for almost the entire history of the universe. Roughly 380,000 years after cosmic expansion began, the universe had cooled enough for free electrons to join atomic nuclei. Before then, light scattered repeatedly from charged particles and could not travel far. Once neutral atoms formed, the universe became transparent, allowing the radiation to move through space. At that time, the radiation had a temperature near 3000 Kelvin. Its wavelengths were much shorter, and much of its energy occupied visible and infrared parts of the spectrum. Cosmic expansion has stretched those wavelengths ever since. As space grows, the distance between successive peaks in each traveling wave increases. A longer wavelength means a lower energy photon, so the entire background radiation field cools. Its temperature falls approximately in inverse proportion to the cosmic scale factor, a quantity astronomers use to describe how much the universe has expanded. If the scale factor doubles, the radiation temperature falls to about half its earlier value. Today, the cosmic microwave background measures close to 2.725 Kelvin. Expansion will continue stretching its photons, pushing their wavelengths farther into the radio spectrum and lowering their temperature towards still smaller values. Stars create temporary exceptions within this larger cooling trend. A main sequence star compresses matter strongly enough for nuclear fusion to occur in its core. Hydrogen nuclei combine into helium, releasing energy that travels outward and eventually escapes as radiation. This creates a steep temperature difference between the hot interior, the cooler surface, and the surrounding space. Those gradients make work possible. Starlight warms planets unevenly and drives weather. Chemical reactions proceed because energy flows from concentrated sources into cooler environments. Life on Earth depends on this continuing movement of usable energy. Every star carries a finite fuel supply. Massive stars consume theirs rapidly and may survive for only a few million years. Smaller stars burn more slowly. Red dwarfs, which use their hydrogen with remarkable efficiency, may continue shining for trillions of years. Star formation will also decline as galaxies use, disperse, or lock away much of their available gas. New stars will become less common, while existing ones complete their lives and leave remnants behind. Stars similar in mass to our own eventually produce white dwarfs, dense objects containing roughly a stellar mass within a body about the size of Earth. With no sustained fusion in their interiors, white dwarfs gradually release stored thermal energy and grow colder. More massive stars can leave neutron stars, objects so compact that a teaspoon of their material would have an enormous mass under Earth gravity. Neutron stars begin extremely hot and cool through radiation and the emission of nearly massless particles called neutrinos. Their remaining heat continues fading over immense periods. Black holes introduce an even longer clock. According to Hawking radiation, quantum effects near a black hole allow it to lose mass gradually. A black hole with several times the mass of a star may require around 10 to the 67th years to evaporate. The largest known black holes could persist toward 10 to the 100th years. Predictions across such extreme times depend on physics that cannot be tested directly. The possible decay of protons, the behavior of dark energy, and unknown quantum gravity effects could alter the distant sequence. The broad thermodynamic direction remains clearer than the details. Concentrated energy tends to spread into forms that are less able to perform useful work. Entropy is the physical quantity used to track this dispersal. A state of higher entropy contains fewer accessible differences that can drive organized change. Heat death describes a possible future approaching maximum entropy. Temperature and density differences become increasingly rare, leaving little usable energy available to power complex processes. Microscopic particles may still move, and radiation may continue crossing space. The decisive loss concerns gradients, the differences between hot and cold, dense and thin, concentrated and dispersed. Warmth throughout cosmic history has existed in organized pockets created by collapsing matter, nuclear reactions, and stored energy. Each pocket lasts for a limited time before its energy spreads outward. One small spacecraft can display the same process on a human scale. Its power source weakens, its internal gradients narrow, and the machinery preserving warmth eventually stops. Long after the final command reaches the spacecraft, its temperature continues changing. The cabin is empty. Ventilation fans no longer move air through the passageways. Coolant pumps have stopped, and the transmitter sends no signal toward Earth. No computer remains awake to compare sensor readings or decide which heater should receive the last available watts. The vehicle does not cool as one object. Thin exterior panels lose energy first because they have little thermal mass. Thermal mass describes how much heat an object can store before its temperature changes. A lightweight antenna support may cool quickly, while a thick tank wall or dense block of electronics can remain warmer for much longer. Deeply insulated equipment bays respond slowly. Their blankets reduce radiation loss, and the small points connecting them to the outer structure limit conduction. Heat stored in circuit boards, metal housings, batteries, and trapped fluids continues moving through those contacts. Each component has its own thermal time constant. This is the characteristic period over which its temperature responds to a change in heating. A small exposed sensor might approach its new condition within hours. A protected tank or heavy structural section may require days, months, or longer. The remaining batteries release the last of their chemical energy. Some cells may discharge through internal leakage after they can no longer operate equipment. Fluids cool toward their freezing points. Metals contract by slightly different amounts, leaving stress locked into bolts, joints, and soldered connections. Radioisotope fuel continues producing heat after every electrical system has failed. Plutonium-238 has a half-life near 87.7 years, so centuries pass before its thermal output becomes only a small fraction of what it was at launch. That warmth spreads through the generator housing and mounting structure. Nearby surfaces remain slightly warmer than distant sections of the craft. The difference grows smaller with every passing decade, but no single moment marks the freezing of the entire vehicle. Infrared radiation continues, carrying energy away whenever a surface remains warmer than its radiative equilibrium temperature. Equilibrium arrives when the absorbed and internally produced power approaches the power being emitted. The result differs across the spacecraft. A dark surface with high infrared emissivity releases heat efficiently. A polished surface retains it longer. Orientation determines how much distant starlight reaches each panel. Galactic infrared radiation, the cosmic microwave background, and occasional particle impacts provide weak but continuing inputs. No universal final temperature spreads through every material. One side may face a brighter field of stars, another may remain shielded behind the main body. Residual radioactivity can preserve a small internal gradient long after the electronics have become unusable. The machine continues traveling. Cosmic rays pass through its hull and slowly damage molecular bonds. Energetic particles alter electronics that will never operate again. Microscopic dust impacts leave tiny craters in exposed surfaces. Repeated heating from distant stars may become possible during rare passages through brighter regions, followed by long intervals of cooling. Most of the structure can survive for immense spans of time. There is no oxygen-rich weather to rust it quickly, no rain to erode its panels, and no living ecosystem to break its materials apart. Change continues through radiation, impact, and the slow behavior of matter itself. Deep space, cold, gains its power through patience. It provides no warm atmosphere to distribute energy, no external fuel supply, and no natural system that repairs failing machinery. Every heater depends on finite power. Every pump eventually stops. Every battery reaches the end of its useful chemistry. For a while, coolant moves through narrow pipes. Instruments remain within carefully protected temperature ranges. People breathe inside a manufactured climate held together by insulation, electrical power, and continuous control. Later, the same spacecraft continues between the stars without active warmth. Its silent structure remains a physical record of the place that built it. Somewhere far behind, around an ordinary star, matter gathered into oceans, cells, minds, and machines. One of those machines crossed into the dark, carrying evidence that a living world had once been warm enough to send it there.